Okay, guys. Sorry for the short delay. So we are, I guess, officially at the second half of the semester. So congratulations for surviving so far. I didn't finish all of Newton's method last time. I didn't talk about Newton with equality constraints, so I'm going to do that now. And let's hope I can pivot over to our slides on the barrier method, which is most of today. My escape key is actually broken on my computer, so I'm just trying to get out of this full screen presentation in some way, but we'll get there eventually. So equality constrained Newton. Last time we learned Newton's method. And a very important special case, or let's say extension rather of what we learned, is Newton for equality constraints. So our problem is, let's say, minimize some convex twice differentiable function f subject to some equality constraints ax equals b. And there are, roughly speaking, three ways to approach this. Okay? The first thing you learned a long time ago, probably at the second lecture or somewhere close to that, which is to reparameterize the problem so it's unconstrained. So pick some matrix F whose columns span the null space of A. Okay, pick some point x0 that satisfies the equality constraints, ax0 equals b. And then realize that you could write every x that satisfies this constraint as f times y plus x0 for some y. Okay, unconstrained, really for any y. Right, because if I multiply through by a, I get ax equals afy plus ax0, and this afy is going to be 0 because by construction the columns of f span the null space of A, and ax0 was b by construction. So any point of this form satisfies the constraints. And so we just replace all appearances of x above with fy plus x0. We don't have any more equality constraints. And we minimize f of the quantity capital Fy plus x0. So that's one way to approach that. Why would that often not be a good idea, let's say, with Newton? Why could that not be a good idea with Newton's method? What problems would that potentially pose? Let's suppose the Hessian of f was very nice. Okay, let's even suppose it was diagonal. Okay, which means that the linear systems we have to solve in Newton's method, just to go back, right? Newton's method repeats updates of this form. If the Hessian is diagonal, this is a trivial linear system to solve. So solving for this direction is very, very cheap. What's the problem with doing something like this? Let's say for a generic matrix A. Well, what would the Hessian be? Okay, if my function was f of fy plus x0, if that was g of y, what would the Hessian be now? Okay, it's just the chain rule, and I'm going to assume everyone's shy because it's a Monday or something. This is just using the chain rule. Okay, and if this had a nice structure, let's say an f was computed via like an SVD or something, then this matrix could actually be dense. This whole thing could lose whatever the structure I had in the Hessian in the first place. So let's suppose the Hessian was diagonal, and I was going to be using Newton's method because it has fast convergence, and also because with a diagonal Hessian, the steps are really fast. But if I were to reparameterize to get rid of equality constraints, then I would likely, let's say if I just use the SVD to compute the columns of f, I would likely have a dense Hessian in the reparameterized problem, which would be a lot more expensive. So that's going to be destroying any structure we would have had in the problem. Okay, how about another thing to do would be to derive the dual. So you can check that the dual function, okay, the Lagrange dual function associated with this problem is this guy. This actually follows just calculations with conjugates like we did a couple lectures ago. It's the negative conjugate of F evaluated at minus A transpose V minus B transpose V. Okay, so this is good because now if A was structured, okay, if A was structured, there'd be no reason to think that F would be structured, because if we're just computing F with an SVD, again, somehow it's out of our control. We can't really find a nice null space parameterization. But if A was structured, okay, then at least now we have what looks like an unconstrained problem. The dual is to maximize this. And if we could compute the conjugate of F, then we could probably use Newton's method on the dual. And with some luck, we could express the primal solution in terms of the dual solution. So that is always an option, to go to duality. And we'll see more when we talk about a method called dual decomposition in a couple of, maybe several lectures. But perhaps the most straightforward option is just to use Newton's method with equality constraints. And that's what we're going to introduce right now. Okay, so it's a good idea in the sense that it's going to use whatever structure there is in the Hessian of F and use whatever structure there is in A to try to take Newton's steps as efficiently as possible. Okay, so it's really the same idea as Newton's method, okay, which is that we're going to make a quadratic approximation to our function. So this is our function, let's say, around the current iterate at f, or this is a quadratic approximation to our function around the current iterate x. Right, I'm leaving out f of x because I'm thinking about this as a function of z, and that term is a constant. And then the usual Newton's method would just minimize this quadratic approximation over all z, and that would define our step direction v. Okay, and you'd see that the solution is negative Hessian inverse the gradient. This is the motivation for Newton we used last lecture. For equality constrained Newton, okay, it's just a very small change. First, we're going to start with a point that's feasible. So we're going to find some point that satisfies the constraints. AX0 equals b. Okay? And every step we take from the first iteration on, we're going to make sure has every step v has the property that a times v is going to be equal to 0, which means that we're going to be adding something to our iterates, but that thing is going to have it's going to have 0 product with a. So our iterates are always going to satisfy the constraint a times x equals b. So all I'm doing is I'm putting as a constraint, okay, as a constraint in this optimization problem that determines my update that az equals 0. Okay, hopefully this makes sense to everybody. And look, we actually went through this case specifically when we talked about the KKT conditions. This is minimizing a quadratic. This is a quadratic function of z, right? Think of x as fixed, subject to equality constraints. And we know that we can use the KKT conditions to write down necessary and sufficient conditions for the solution here. Convex quadratic, subject to equality constraints. And if you go back to those slides, you'll see we just had to form the Lagrangian. There was a dual variable that corresponded to this constraint. And we could combine together stationarity condition and primal feasibility into one condition. And that's this linear system right here. Okay, so this big system expresses both the stationarity condition and primal feasibility. So we call this oftentimes the KKT matrix associated with this problem. Okay, so go back to those slides if you are fuzzy on how we got this. Okay, but the solution to this problem is determined by solving this linear system. Okay, and it's just a little bit bigger than the solution to the unconstrained Newton system. Right, so unconstrained Newton, we have to solve this system. Right, Hessian times some direction v is equal to negative gradient. And constrained Newton is a bit bigger. Okay, so we solve for v and w together. And we at least for the purposes of today's lecture, we can discard w. We don't need it because we just care about the update direction. Okay, but if we solve this little bigger system, then we'll get the update direction v that satisfies a times v equals 0 and minimizes this quadratic approximation. Okay, so that's Newton with constraints. And it's really, I guess, as straightforward as that. Everything else that we learned still applies. Convergence rate, backtracking, everything is the same. We just now are going to be staying inside this feasible set. I'll just mention this briefly, and then we're going to have a whole lecture on Quasi-Newton in about a week, I think, or maybe exactly a week. So oftentimes it's expensive to take Newton steps, or it's maybe it's expensive just to form and store the Hessian in memory. Okay, so this is where Quasi-Newton methods come in. Quasi-Newton methods approximate the Hessian by a matrix H that's simpler. It's simpler to store, and it's simpler to solve a linear system in H. So the presumption is that, let's say, solving H times V equals negative gradient is simpler than it is solving the Hessian times V equals negative gradient. And Quasi-Newton methods, I think, they're a beautiful development optimization. They're extremely useful in practice. They lie somewhere in between first order and second order methods. So they don't converge at a local quadratic rate, but they converge at a rate faster than a local linear rate. So that's why we call them superlinear. So they're faster than first order methods. They're slower than second order methods. And computationally, they're somewhere in the middle as well. Okay, so instead of, let's say in the worst case when the Hessian is dense, solving the system would be order n cubed. Okay, solving it with a Quasi-Newton method, the two most popular methods, let's say, it's order n squared. Okay, and a gradient update is typically order n. So they provide something that lies nicely in the middle. And we'll go through that in detail in a week. Okay, any questions on Newton before we move on to the barrier method? Okay, let's hope I can get out of this now. Okay, that worked. Okay, so today we're going to talk about the barrier method. I won't do the recap on Newton because I think we just did that. And this is equality constrained Newton. So let's try to motivate the barrier method. So the barrier method, by the way, is the first of two interior point methods you're going to learn. So we're going to talk about the barrier method today, and on Wednesday we're going to talk about another interior point method called the primal dual interior point method. And I think it's nice to kind of try to situate them in the hierarchy of what we've seen. So let's think about all problems being convex and think about the problems we've seen so far and whether they're easy or hard and how we'd handle them. So quadratic problems are the easiest. Convex quadratic problems are the easiest in some sense problem we've seen. Okay, unconstrained convex quadratics because they have a closed form solution. I just differentiate them, I take their gradient set equal to 0, and I have the solution in closed form after I solve a linear system. Equality constrained quadratic problems are also easy. Okay, we saw that if you have a quadratic subject to equality constraints, you just take the KKT conditions, and that gives you another closed form solution where you solve a bigger linear system. Okay? The next thing we talked about were equality constrained smooth problems. So let's suppose you have, instead of minimizing a quadratic subject to equality constraints, you're going to minimize a twice differentiable function subject to equality constraints. This is where Newton's method comes in. It actually reduces, okay, every single, it reduces this problem, let's say, minimizing f subject to equality constraints, to a sequence of quadratic minimization subject to equality constraints. Right? So Newton takes f, turns it into a quadratic, leaves the equality constraints alone, and then we have a closed form solution to that. That was just equality constrained Newton that we saw. So they brought us back to an easy case. Okay, where are we now? We're thinking about smooth functions. This now we're getting very general. Smooth functions, so let's say twice differentiable functions, subject to equality constraints, but also subject to inequality constraints. And currently we don't know how to handle those. Okay, we only know how to handle those in one way that we've learned so far, and that's projected gradient. Okay, if we could project onto the constraint set, so equality constraints intersected with a bunch of inequality constraints, then we can use projected gradient. But as I mentioned somehow a while ago, projections number one are, they're often not easy to do. Okay, so that's not something we can typically do, let's say in generality, only for kind of nice constraints. And number two, we would lose the convergence of Newton's method. So we'd go back to the first order convergence. Okay, so that's where interior point methods come in. They are going to reduce inequality constrained problems to a sequence of only equality constrained problems. And it brings us back to case 3, where we have smooth functions subject to equality constraints, in which case we can apply Newton. Okay? Was there a hand up somewhere?
Oh, I was going to ask about slack variables, but if you have non-convex function, it doesn't work. So.
Well, we're talking about convex problems, but
if you have a non-convex inequality constraint, that's valid.
yes, that's right. Yeah. Okay, so that's where we're situated right now. So let's talk about the simplest way to proceed, which is with an interior point method called the barrier method. And we're going to do exactly what I said, which we're going to take a bunch of inequality constraints, and we're going to essentially push them into the criterion, okay, in a smooth way, and reduce the problem to an equality constrained smooth minimization problem. So let's suppose we have a problem of this form, okay, where all my functions f and hi are convex and twice differentiable, and they have full domain. So this is really just for simplicity. You know, they could actually have, you know, say domain that's a proper subset. And we're considering minimizing this problem. So the difference to what we saw with equality constrained Newton is actually just these guys, these inequality constraints. So associated with this function, we can define a function phi that we call the log barrier. And the log barrier, it is defined as the negative sum of the log of negative hi of x. So I take all of the inequality constraint functions. I negate them because, right, for feasible points, there should be negative. And so I have to negate them to pass them to log. Otherwise, this wouldn't make sense. I add them all up, and I take the negative. And I'm going to motivate this in just one slide. So we'll see where this comes from. But for now, you know, we'll just observe that this function, its domain is the set of strictly feasible points. So it's not defined if any of the hi's are active, if they're equal to 0 at x. Okay, but it's defined on the set of all x for which all of the hi's are strictly less than 0. Okay, we're going to assume that this is non-empty. This set is non-empty. And note that actually that assumption implies that strong duality holds. Right? Because I have a convex problem. I just told you that the inequality constraints could be satisfied strictly. Slater's condition tells us that therefore strong duality holds. Okay, so if we were to derive the dual, we would see that actually its optimal value equals the primal optimal value. So let's ignore the equality constraints and try to motivate the barrier the barrier function we just defined, the log barrier function. If we ignore the equality constraints just for motivation's sake, then as we've seen several times before, we can always push up constraints into the criterion via indicators. That transformation is lossless. We can always do that. And so I can always add the indicators that, you know, every hi of x is less than or equal to 0. In one dimension, let's suppose that let's suppose I'm in one dimension and I have one function. That's like this dotted line. Okay? So let's suppose that that indicator function is just this dotted line. Okay? We can approximate this smoothly by approximating the indicator function by negative log of negative x. That gives us a smooth approximation to the barrier, to this indicator rather, okay, which is often called a barrier in the context of interior point problems. Okay, so this thing right here, phi of x, right, was just minus the sum of log minus hi of x. And if I were to, let's say, multiply phi by 1 over t, okay, which is what I'm doing here. This is just f of x plus 1 over t times phi, where t is some very large number, then that's giving me a smooth approximation to this problem, right, to this problem, which is equivalent to having the hi's as inequality constraints. And the larger the t is, the more accurate this approximation is, right? Because you can think about like I'm really only smoothing for very large t this indicator only a little bit. Okay, that's the motivation for that function. So today we're going to talk about how to use that idea, this log barrier function, and the fact that it approximates the indicator to define something called the central path. We'll talk about properties and interpretations of the central path. We'll introduce something called the barrier method, which is the first interior point method you'll learn. We'll talk about its convergence, and if I have time, I'll mention something called feasibility methods. So for what we're going to do coming up in the lecture, it's helpful to do a bunch of calculations with the barrier function. Okay, because, I mean, maybe I've already said this. We're going to do essentially Newton's method on this. Okay, on this criterion. And we're going to need to know things like the gradient and the Hessian of phi as a result. So we're just going to calculate those to have them in hand. And this is all just the chain rule. So I'm not really going to go through these carefully. If you're confused about any of these expressions, then I would definitely recommend you do these yourself, because when you're dealing with interior point methods, you'll be needing to work with functions of this form frequently. So you want to get comfortable with its Hessian and its gradient. Okay, so the gradient, right? I can just think about taking the gradient of each of these terms, and the gradient of log of x is 1 over x, so I'm just using the chain rule. It's 1 over hi of x times the gradient of what's in the middle, which is it's negative hi of x, negative grad hi of x. And for the Hessian, okay, I just have to take the derivative of this, and I'm just using the product rule actually here. So if I differentiate this, right, then I get 1 over hi of x squared times the derivative of this, which gives me a grad hi of x transpose. And the other part of the product rule is to leave this alone and differentiate this, which gives me the Hessian. So this is the Hessian of hi itself. Okay, so this is the gradient, and that's the Hessian of the barrier function. So what is the central path? The central path is defined as a solution essentially to this problem, okay, where we've kept the equality constraints, but we've moved the inequality constraints up into the criterion via this trick that was a smooth approximation to the indicator. And I've just multiplied actually the whole criterion by t, just really for convenience. So it's equivalence to this. Right, so the problem is to minimize t times f of x plus phi of x subject to ax equals b. Phi is that log barrier function. F was our original criterion. These were our original constraints. And we denote the central path by x star of t. Okay, thinking about this as a function of t. The hope is that if we make t really big, okay, we're going to have that the central path solution approaches the solution to our original problem, right? Because then we have this thing where as t gets bigger and bigger, we have this indicator function that we've been smoothly approximating. It's a better and better approximation. It looks more and more like the indicator, right? So eventually we should get that this problem is so close to our original constrained problem that the solutions coincide in the limit. Okay, so once you see this, the first thing you might think is, why don't we just set t to be some huge value, like take t to be as big as I can imagine, and just directly seek the solution at the end of the central path. So, I guess by saying the word path, we're thinking about this as t varies. You might ask, why am I even thinking about it as t varies? I'll just take it for a large value of t. That'll approximate the solution. The problem is that this is seriously inefficient in practice for two reasons. The first is that this becomes very numerically unstable if I just take a huge value of t, okay? Because as you can imagine, in either formulation, either multiplying this by t or multiplying this by 1 over t, it's not numerically stable. And the second problem is that if you were to do something like Newton's method on this, it would actually take Newton's method a while to get into the quadratic convergence phase, it just turns out, for this problem. If I take t to be very big and I start from somewhere arbitrary like 0. So it won't be very efficient. Okay, you will be trying something that maybe makes sense in principle, but in practice is going to be very efficient. In practice and also in theory, it's much more efficient to efficiently traverse the paths. So actually solve this problem at a bunch of intermediate values of t, use a solution at one value of t to warm start the algorithm at the next value of t. So that's really what we're going to do. Apply Newton's method over a sequence of t's. Every time we solve it, we're going to pass the solution as a warm start to the next value of t, each time making t larger. And what we're going to do, you can think informally, is that what this is doing informally is that it's always keeping Newton's method in the quadratically convergence phase. So when t is small, it's actually much easier to solve this problem. Okay, maybe it's more numerically stable. We can solve this efficiently. Also because the barrier function is very smooth. It actually has nice derivatives and a nice Hessian. And then we're going to warm start Newton at a little bigger value of t. And if we do so carefully enough, then we're going to keep Newton in the quadratically convergence phase. So it's not going to take very many iterations until it's allowed to take full step sizes, like the pure Newton. And it's going to converge very fast. We'll make t bigger. The warm start will help us get into that pure Newton phase. It'll converge very fast, etc. That's informally what's going to happen. So an important special case is the barrier problem for a linear program. I think this has a very nice interpretation. And also, this picture is going to explain to you the name interior point method. It's also true in general, but the same motivation or intuition will hold in general. We're actually approaching the constraint set from the interior, but for a linear program, it's even more explicit. So let's suppose I had a linear program, right, of the form minimize, let's say C transpose x, subject to dx less than or equal to some vector e, which I'm going to write as, I can also write as di transpose x less than or equal to ei for a bunch of i's, I equals 1 to m. So the central path problem corresponding to this linear program, right? We're going to rewrite this again as maybe ei minus di transpose x bigger or equal to 0. The barrier function is negative log of the sum of log of ei minus di transpose x. That's the barrier function, right? Corresponding to this problem. And that's what I'm showing you up here. This is the barrier problem. T times the criterion plus the barrier function, negative sum of log of ei minus di transpose x. Okay. For this problem, I didn't put any equality constraints down, and it has a simple form. You can just check that by taking the gradient and set it equal to 0, okay, because it's a convex problem. I guess that would be an important thing to point out. Maybe I should do that now. This is a convex function. It's going to, yeah, that would have been an important thing to point out, that this is a convex function. Okay, you can check this in various ways. I guess it's easy to see directly for this linear program. Okay, I mean, because log is concave, and now I'm composing log with an affine function. So negative log is going to be convex. Okay, so this is a convex problem. I can just take the gradient and set it equal to 0 to get the optimality condition. This is what it looks like. Okay, t times c, that's the gradient in this part, minus taking the gradient of these gives me 1 over what's the inside, ei minus di transpose x star, times the gradient of what's in the inside, and that's just di. This is the optimality condition. Okay, and what this means is that the gradient, okay, this is the gradient of my log barrier function at the solution. It must be parallel to minus c. So if you look at this picture, okay, I'm not sure what's the best thing to do here. If I can, yeah, I can zoom in. So if you look at this picture, okay, this is, let's say, the polyhedron. That's my constraint set. So this polyhedron is the sum of is the set of all x's for which di transpose x is less than or equal to ei for all I, and the barrier function, okay, the contours of the barrier function are being drawn here. What the optimality condition tells me is that at the central path solution, so at some value of t, here t was 10, okay, the gradient of the log barrier function, okay, it points in a direction that's parallel to the criterion, the vector, the gradient of the criterion, minus c. So it's pointing us in the direction, okay, that maximally reduces the criterion. okay, subject to all points having the same barrier value, log barrier value. Okay? And we're going to end up at a vertex, right? Generally speaking, any linear program is going to have its minimizer at a vertex or along one of the faces, but more often at a vertex. And we're going to arrive there, okay, by minimizing a sequence of smooth problems, each of which approximates the polyhedron by this smooth constraint region. Hence the name interior point method. Okay, so that's the motivation for the barrier problem for linear programs, which is a very common case. So let's now characterize optimality for the central path problem via the KKT conditions. Okay, and we're going to see that a bunch of interesting things come out. So the KKT conditions for this problem, okay, for this problem right here, that's what we're writing down, are as follows. The first one is just stationarity. Okay, so this is the gradient of the criterion. This is the gradient of the log barrier function. Remember, we had derived that earlier. And this is so the dual variable w is what appears because of my equality constraint ax equals b. And so this is now going to be the gradient of the linear term w transpose ax minus b that I would get. So this is stationarity. Okay, and this is primal feasibility, and that's dual feasibility. Sorry, this is all primal feasibility right here. Okay, we don't have dual feasibility, we don't have complementary slackness because we don't have any inequality constraints anymore, right? We've gotten rid of them, so we just have equality constraints, and so we just have primal feasibility. And if we could solve this, let's say for some x star and for some w, then we'd have the solution to the central path problem. But we don't really care about this w. Okay, this w serves really no purpose other than kind of giving us a solution to the central path problem, because if we could solve this for x and w, we'd get the solution to x in this problem, which we do care about, and we get the solution w and the dual of this problem, which doesn't really matter to us, right? We don't care about the dual of this problem at this point. We only care about this problem in so much it approximates the original problem. What we really do want, let's say, maybe because we want to calculate a duality gap, is to figure out a dual variable that's feasible for a variable that's feasible for the dual of this problem, right? Because oftentimes the dual is going to be useful to us in terms of computing a duality gap. So if we had x star from the central path, it would be feasible for this problem, but we don't yet know a feasible dual point. So we don't really know how to somehow measure how far we are away from optimality having solved the central path. Right? So solutions of this are feasible for the original problem by definition, that the barrier function is only defined on the feasible set. But we don't know yet what a dual feasible point would be for the original problem. And turns out to be a very simple answer. Okay? If you were to solve the KKT conditions to get x star and w, we could then just define dual variables u and v. Okay, u are going to correspond to the inequality constraints, and v to the equality constraints, as follows. So v I'm going to take to be the w that I got from the KKT conditions divided by t, and u is going to be negative 1 over t times hi of x. Those are two definitions of variables at this point. Okay, and what we're going to see is that they're actually dual feasible for the original problem. Okay, which in other words means that they're going to lie in the domain of the Lagrange dual function. So why? Well, first, let's just notice that as we've defined them, ui is going to be strictly positive, because remember the hi's were strictly negative. So minus 1 over t times hi is going to be strictly positive. So that's good. Remember, we need at least this signed constraint on u. And furthermore, this point lies in the domain of the Lagrange dual function, meaning that it's not infinite at that point, or negative infinite, because by definition, if we just were to plug in these 2 points, okay, plug in these 2 points here in the definition of stationarity, you're going to see that this is just exactly ui times the grad of hi, actually times also a t, And this is just going to be exactly t times A transpose V. All the t's will cancel, and you get this condition. So this is just plugging in for u and v in the stationarity condition we got for the central path problem. Okay, and if you look at this, this is actually stationarity for our original problem. This is the stationarity condition for our original problem, right? That had constraints hi of x less than or equal to 0 and ax equal to b. So what we said is that at the point x, okay, or rather at the point u and v, x minimizes the Lagrangian. Okay, and because x minimizes the Lagrangian at the point u and v, we know that it's not going to be ill-defined there. Okay, it's actually going to be strictly away from negative infinity. So all this was just to say that this definition gives us feasible dual points for our original problem. And that's a very helpful thing to know, because now we can compute a duality gap. Okay, we can take the criterion, let's say, at x star of t. We can take the dual criterion at u star of t and v star of t. We can take the difference between the primal and the dual. That'll give us a bona fide duality gap for the point x star of t for the original problem. Okay, so the plugging in for the, let's say, the dual criterion at the point u star and v, well, as we said, that was just going to be equal to the Lagrangian evaluated there, because we know that the Lagrangian at u and v is minimized at x as we've defined it. And just looking at how we've defined this, okay, this is going to be 0, right, because x is going to meet the equality constraints. ui, remember, is defined to be minus 1 over t times hi, so I get minus 1 over t when I multiply them together, and I have m of them, so the total is just minus m over t. So the dual function evaluated at these points u star and v star that we formed is just f of x star of t minus m over t. M's the number of constraints here. And if I take the difference now between, let's say, the primal, which is f of x star of t, and the dual, I just get m over t. So that is the duality gap. In other words, I know that if I were to solve the central path problem, I've guaranteed now, through duality, that I'm no farther away from optimum than m over t, where m's the number of constraints. Okay, so I guess this is just to back up another example of some very simple calculations. There was nothing super complicated here. It might have been a bit, let's say, complicated that we're switching between the barrier problem and the original problem, but modulo that, there is nothing complicated we've done. And we've arrived at a very powerful conclusion, which is that the solution to this problem, this barrier problem, okay, gives us a duality gap of m over t to a solution to the original problem, where m's the number of constraints. Super easy to calculate. So once I solve this problem, I know exactly how far away I am away from optimal. It's m over t. Okay. Aside from being useful as a stopping criterion when we actually describe the barrier method, it also confirms our hope, right? That as t approaches infinity, we're going to get the solution to the barrier problem approaching the solution to the original problem, because the duality gap is going to 0, right? M over t is going to 0. So this proves that actually this construction will recover the solution to our original problem in the limit. Let me pause for questions to see if people have questions about this step. Okay. So, okay, we're just going to learn one more thing, and then we can take our break. This is a very, it turns out, useful alternative interpretation of the central path. So one interpretation of the central path is what we did so far. Okay. The other one is a little different. It turns out it's an alternative motivation entirely for the central path. And we're going to see that actually, starting here, we can get to the barrier method. We can also get to the primal dual interior point method. So this is going to, once we kind of think about this differently next time, we're going to actually arrive at a different algorithm than the barrier method. So let's look at the central path, okay, as solving a particular set of equations that we can see as perturbed KKT conditions. So I'm just taking the KKT conditions for the central path problem, this one, and I'm reparameterizing them, as we've done already, by defining ui to be minus 1 over thi. Just introducing that variable and writing down the KKT conditions in that notation. And as well, I'm introducing the variable v to be w over t. Okay? With that, the stationary condition, as we've already seen, becomes this. Grad of f of x plus the sum of ui hi of x, or grad hi of x plus a transpose v. What is this? Just once more, this is just stationarity for our original problem. So this is a familiar condition. Okay? By construction, okay, I've introduced ui by construction to meet this constraint. Ui times hi of x is equal to minus 1 over t, right? Because I just defined ui to be minus 1 over t times hi of x. All of these hi's has to be less than or equal to 0. That's true from the central path KKT conditions. It actually gave us a strict inequality. Ax equals b, also true from the central path equations. And all of the hi's have to be bigger than or equal to 0. Okay, that's actually just implied by these two constraints. Right? The fact that hi is less than or equal to 0, u times hi is something negative implies this one, but I'm writing it down anyways, somehow just to for emphasis. So if you stare at this, this actually should look very similar to the KKT conditions for the original problem. Right? The KKT conditions for our original problem, okay, for this guy, min f of x the KKT conditions are going to be stationarity, which we have. Okay, it's going to be complementary slackness. It's going to be primal feasibility and dual feasibility, which we have. Okay, stationarity, primal feasibility, dual feasibility. Complementary slackness, okay, is the one offender here. Instead of having the typical complementary slackness, right, which is that ui times hi of x is equal to 0 for all I, we have what you might interpret as a perturbed version. Ui times hi of x is equal to minus 1 over t. Okay, if it's not going to be 0, we know it has to be negative because hi of x is less than or equal to 0. Ui of x is bigger than or equal to 0. That's primal and dual feasibility. So if it's not 0, it has to be something negative. And it turns out that the central path is the solution to the KKT system once we replace complementary slackness with this perturbed version. We've replaced 0 by minus 1 over t. As t gets very large, okay, as we take t to be very, very big, this approaches complementary slackness. So solving this system is going to give us a solution to our original problem. So if we didn't have any barrier function whatsoever, look, there's no appearances of any barrier function whatsoever. I haven't had any appearances of phi. Everything here is defined in terms of my original problem. I could have motivated the barrier problem by taking the KKT conditions and just changing complementary slackness from this to this. I would have arisen at the same object, which is the solution to the central path. So it's entirely alternative motivation to the central path. And just to repeat, as I said, next time we're going to start here when we talk about primal, dual, interior point methods, and we're going to actually see that we can fork off in a little different way from here and get to a different interior point method altogether that is more often used in the barrier method. It's more complicated, but it's more often used in the barrier method today. It's much more common. All right, let's take a quick break, and then we'll come back and actually describe the barrier method in full. So what we do is we fix an initial value of t, call it t0, and we fix something that we call the barrier parameter, mu. Mu is some constant larger than 1. And we're going to use Newton to compute a solution to this problem at the value t equals t0, and call that solution x0. That's our that's what we call the initial centering step. So every time we solve this problem, we call a centering step. This is our initial centering step. And the method proceeds as follows. We then, I should have probably multiplied, I should have defined T1. Am I not multiplying at all by T? Oh, I'm doing the update here at the end, which doesn't, I guess, make as much sense. But I should have written here something like update Tk to be mu times Tk minus 1. That probably makes a bit more sense as I've written it. It is kind of more or less equivalent, but I guess I haven't defined T1 as it's written. So maybe think about that as the first step. So we'll take the previous value of T. Like let's suppose we started at T equals 1 and mu was 5. So we multiply by mu. We get, now we're solving the problem at 5. Okay, next time we're solving at 5 squared. Next time we're solving at 5 cubed, etc. And we're going to solve that problem with that new value of T, Newton's method, initialized at the previous centering step estimate, so at xk minus 1. And we're going to stop if m over t is less than epsilon. Okay, as we keep getting bigger and bigger t's, we can just stop whenever m over t is less than epsilon for some predefined epsilon that's going to be our suboptimality gap, right? This controls how far we are away from optimum. Okay, so what are some considerations for this method? There's really only two, because it's just Newton's method in sequence. So all the considerations for Newton's method, but that's pretty well defined. We just use Newton with backtracking. Then there's two kind of considerations for the outer iterations, right? So you're going to have two levels of iterations. One is the iterations that go on inside Newton's method. Those are called inner iterations. These are the outer iterations, the ones that kind of call Newton's method in sequence. And the considerations for those are just choices of mu, the barrier parameter, and choice of t0, which is the initial value of t. And it's a bit obvious, let's say, somehow what the effect of different values of these parameters are. If mu is too small, then you're going to take a lot of outer iterations. So you're going to probably have more outer iterations than you would desire. Okay, if mu is too big, then it's possible that you wouldn't be warm starting Newton good enough. Okay, because you've moved from t to like 100 t, and maybe now the solution to that problem is different, fairly different from what it was when you had t. And so by warm starting Newton, it's going to take a while to get into the quadratic convergence phase, and it would take too many iterations to converge. So that's the trade-off with mu. The trade-off with t is similar. If you take t to be too big, then this is the problem that we described initially. If you take t to be huge, then you're going to have too many Newton steps to begin with. If t is small, then you're probably going to be needing many outer iterations to get to a highly accurate solution, because it's going to take you a while to get to a very big value of t. The beauty of interior point methods, this is also true with primal dual interior point method, is that their performance is quite robust to these outer iteration parameters. So it's pretty remarkable how they're not super strongly affected by the choices of these parameters in practice. That is one of the reasons why interior point methods are so kind of ubiquitous in these big commercial solvers. If you want to solve a QP, let's say in practice, or an STP in practice, and you wanted to use like the state-of-the-art optimization for generic QP, generic STP, generic LP, nothing special about those problems, like no special structure, you'd probably use something like Cplex or Gurobi or Sudumi. These are these big commercial packages which are free for academic use, and they're going to implement interior point methods. There's not a lot of fiddling they have to do with these parameters because their performance is typically quite robust to them. So here's just an example of that. I took this from the Boyd and Vandenberg textbook. It's kind of a small linear program, 50 variables and 100 inequality constraints. And here's different choices of mu. This is mu equals 2. The Barry method conversion 80 iterations total. So this is counting all of the Newton iterations required. So this is the total number of iterations. So it's a more honest thing to report, right? Because as we vary mu, basically you'll get different behaviors in terms of the number of iterations versus outer iterations. So counting the total number of iterations is the fair comparison. This is mu equals 150, so a much, much bigger value, and that's mu equals 50. So by multiplying mu by a factor of about 100, we saved, half the iterations. But that's really not a huge difference. 40 versus 80 iterations is not a big difference at all. So there's quite a robust performance as a function of mu. And all these are, let's say, bringing the duality gap down to something quite small in a reasonable number of iterations total. So what's the convergence analysis? Well, this is the case where we're going to do a very cheap convergence analysis. Super coarse, and actually it's kind of almost just by definition how we've defined things. And I'm just going to refer you to a more refined analysis, because analyses of interior point methods are substantially more complicated than what you've seen already for, say, Newton or other things. So I don't think it's something that is worth our time to go through in class. So here's just a very coarse result. Let's suppose that I can solve all of the centering steps. So that means each one of these Newton's method calls is done to exact optimality. So I run Newton until exact optimality. Of course, that's not going to be true in practice, right? I'm going to stop Newton at some point. But just for now, let's assume that that's what's happening. Every centering step is done exactly. Then the duality gap after k iterations is m over t. And what is t after k iterations? It's mu to the k times t0. So what's the suboptimality gap after k iterations? It's m over mu to the k times t0. And that means that if I want to reach an accuracy level of epsilon, I'm going to need something like log of 1 over epsilon centering steps. This is really just this is a consequence of our updating scheme for t. That's all it was. Right? The fact that it was multiplicative led to this contraction factor, something to the power of k, as the right-hand side for the suboptimality gap, and then flipped around in terms of epsilon. That's how many iterations I need. Okay, so it's not really telling you why the Berry method works. This is just a consequence of the updating scheme. Okay, but one thing that's important is that this is just measuring the number of centering steps, and I haven't told you about the number of Newton's iterations total, which we saw is an important measure, right? Because we have to actually iterate for these centering steps, and it is actually reasonable in practice, let's say, to assume that Newton will take about a constant number of iterations. So why is that? The details for that are fairly complicated, and that's where I'll refer you to other analyses. And I have a slide, I think it's coming up in a bit, with some more info. But that's actually because of this updating scheme. So a very careful analysis can show that if you were to increase t multiplicatively, then Newton will be, if it was in the quadratic convergence phase in the previous iteration and it converged, and you warm start it with that solution, it'll be in the quadratic convergence phase more or less immediately. So with this updating scheme, that's what we're able to maintain, which means that Newton should require like 5 or 6 iterations to get to extremely high accuracy. So if I tell you the number of outer iterations is this, the number of iterations total is really like 5 or 6 times this. Okay, so it is a fair analysis. Yeah, there's a question.
For that analysis, could we use that to measure what sort of communications so that we can always be as much as possible to still remain in the quadratic motion?
Does the analysis of Newton, you're saying, give us a choice of mu? I kind of doubt it. I mean, it may, but I don't think it would be in terms of quantities you typically have available, or that you wouldn't really want to compute. But like we saw for Newton's method, there's an analysis under self-concordance that is kind of scale-free. So that I'll refer to. And that may actually have kind of more universal recommendation for mu. I just would have to check. I'm not sure. Yeah?
Use the value method with 8% of volume system.
Yeah, it's a good question. The reason is that somehow the barrier method is designed so that every centering step can be done very quickly. And Newton has this property that if we get it in the quadratically convergence basin of attraction or something, that it'll take only 5 or 6 iterations. We could, in principle, apply it with gradient descent as well. But at that point, it's not clear that it's necessarily going to be a better idea than applying Newton. because it will still take maybe many iterations to converge centering steps. All good questions. So here's an example, right, where we're seeing that this is the number of Newton iterations, so the total iterations, not just the number of centering steps. And it's an example of solving different LPs as the number of inequality constraints grows. Okay, and actually, if I'm not mistaken, the number of dimensions, so the number of variables in the optimization problem is growing linearly with m here. So actually, let's say this is a problem with 2 times m variables. So n is 2 times m. And what we can see is that every time, for every LP, we get roughly linear convergence. Right? This is a log plot. This is a log duality gap. And it grows very slowly with m, the number of inequality constraints, okay, which is what we've seen here from this analysis. It should grow very slowly with the number of inequality constraints. Yeah, and this was just another picture for that. This is the number of iterations needed as a function of m to get the duality gap down to some prefixed value, and as a function of m, it's growing very slowly. So we're only kind of let's say paying a very weak cost for having more constraints here. So we already kind of talked about this. We haven't really given a precise analysis about how many Newton iterations it takes, but the analyses that you can find in, let's say, Nemirovsky and Nesterov's monographs on interior point methods, they basically show that this updating scheme keeps Newton in the quadratic convergence phase. So every every call of Newton takes like a constant number of iterations to get to extremely high accuracy. And really the cleanest way that this is stated is in terms of self-concordance. And there's a really very beautiful theory for self-concordance. And I think that the application of self-concordance to interior point methods is the greatest kind of, let's say, achievement of all of the self-concordance theory, because you can really see just how broad the notion of self-concordance is. So I'll mention that in a second. We couldn't quite see that with just self-concordance in Newton. So let's suppose that the criterion function in the barrier problem, which is t times f plus phi, is self-concordant. So that whole function is self-concordant. And our original problem had bounded sublevel sets. So this is a very weak condition. I'm not actually sure whether it's necessary, but that's as far as I can tell. At least that's what's used in the Nesterov and Nemirovsky analysis. Then we can terminate each Newton solve at the appropriate accuracy. So we don't have to assume we're doing perfect inner centering steps. And the total number of Newton iterations, okay, is going to be the same order, log of m over t0 times epsilon, to get an epsilon subaccurate solution, suboptimal solution. And the constants hiding here are universal. They don't depend at all on the function f or the constraint functions hi. They only depend on things like the backtracking parameters that you used in Newton, alpha and beta. Okay, so this is, I think, a very nice analysis. And actually, there's a summary of this in chapter 11.5 of Boyd and Vandenberg, if you're curious. But maybe really the most definitive reference is going to be Nesterov and Nemirovsky's monographs. So when is this self-concordant? When do we have the property that the criterion function in the barrier problem is self-concordant, which is, remember, it's t times f minus the sum of minus the sum of log of minus hi. So that's self-concordant when all of the functions f or hi are linear or quadratic. And that actually now encompasses a very broad range of problems since we're talking about constraints. That means any LP, any QP, and any QCQP, quadratically constrained convex problem, right, which we learned are a special type of conic program that lie in between QPs and SDPs. Any of these problems have a self-concordant barrier criterion, and we can use let's say the barrier method on any of these problems, and we know universally how fast we're going to converge. It does not depend on the kind of specific let's say, condition numbers of the matrices that appear in our problem or the functions that appear in our problem. And I think that's a very kind of very strong and broad result. And this is what underlies a lot of these fast interior point methods solvers in these kind of big state-of-the-art systems. Okay, so the last thing I wanted to talk about, maybe I'll just talk about this quickly, and then if we have any time left, I'm going to tell you a bit about the history of interior point methods. Something I was going to cover next time, but it would be fine to do it now too, and save us more time next time for the content. So we've implicitly assumed that in running the barrier method, we have a strictly feasible point. Right? We need to start off with a point that satisfies all of the constraints, hi of x, strictly less than 0, and also ax equals b. That's not a trivial thing to find. Right? If I give you a bunch of inequality constraints and inequality in a linear system of equality constraints, it's not trivial to find a point x that satisfies all of them. But yet we need this to start the barrier method. This is one of the strengths of primal dual interior point methods, which we actually don't need to start with a feasible point. They can be started at infeasible points. But for the barrier method as defined, we need to start them with feasible points. And how do we find such a feasible point? Well, some people talk about the barrier method running in 2 phases. Phase 1 is just finding a feasible point. Phase 2 is having found the feasible point, solving the sequence of central path problems that you saw to get the solution. And it turns out that actually we can apply Newton sequence in both phases. So really it's just 2 applications of the barrier method. So the first phase, right, we could cast it as an optimization problem. Let's say we introduce a variable s, real valued variable s, and we want to minimize over all points x and s the value of s subject to the constraint that hi of x is less than or equal to s, and ax is equal to b. Okay, if we run the barrier method on this problem, which is itself it has all the requirements needed for us to apply the barrier problem, because we're thinking about solving minimize f of x subject to these constraints, then we can stop as soon as s is negative. Right? If we just run the barrier method, keep track of the value of s through all the iterations, as soon as s is negative, we can stop, because that means we have a strictly feasible point. That is typically called the feasibility method. And there are different formulations. So this is a slightly different formulation, which just replaces s in the criterion, okay, a single value of s, with 1 s per constraint. So here I have hi of x is less than or equal to si, and the criterion is the sum of the si's. And I can stop when all of them, let's say, are negative. I'm not sure why I put I can stop, let's say, when the criterion is 0 here in this example of the problem, because I've put s bigger than or equal to 0. And sometimes, let's say, if the barrier method fails to find a solution here with a negative s, you might try solving this problem instead, because now you struggle to find a strictly feasible point. If you run this for a bunch of iterations and you see that a bunch of the si's are 0 and some of the other si's are non-zero, are positive, then it tells you which of the constraints is hardest to satisfy. So this will actually indicate for you maybe if the system is infeasible entirely, or you can't find a strictly feasible point entirely, why that is, which are the kind of offensive constraints, by looking at a different si per constraint function. Okay. So I guess just I can end in 5 minutes, just give you a quick history of interior point methods, because I think it's fun. We can end a bit early. So this is in our, if you want to look at the slides, it's for the slides for the primal dual interior point methods. I'm just going to jump to the history portion. So interior point methods, maybe, like, to put it succinctly, they were to, let's say, our parents' generation what first order methods and SGD is to our generation. So everybody now talks about first order methods, and now it's getting more about stochastic first order methods, right? And we're going to see a lot of development in that area. Everybody's excited to use them and to prove new things about them and to develop new extensions of them. That was what interior point methods were, let's say, to the people who studied optimization 1 generation before us. And there's a really, I think, very beautiful and interesting sequence of papers that came out. And so here's just a kind of a glimpse of that in case you're interested. So in some sense, it actually all started with George Danzig, okay, who invented the simplex algorithm. The simplex algorithm is an algorithm we didn't learn in this class. It's an alternative method for solving linear programs that is not an iterative method like interior point methods. And it's actually unlike any algorithm we've learned so far in this course, because every algorithm we've learned so far in this course is what people in optimization call indirect algorithms. So you give me some epsilon, I'll iterate until I have suboptimality less than or equal to epsilon. The simplex method, let's say if you had a perfect computer, it would find the exact solution to an LP. It's not iterative in that sense. There's no suboptimality gap you're passing it. It's going to, maybe in a word, bounce from vertex to vertex of the constraint set until it finds the solution. But it's going to do so in a very clever way. And so it's a very unique algorithm because, let's say, with perfect computational resources, you'd have the exact solution. There's no iteration like there is in gradient descent or Newton or interior point methods. OK, the simplex method, unfortunately, there are instances, let's say, for linear programs with n variables where the simplex method takes 2 to the n iterations. So it's not a polynomial time algorithm. And when people saw this, there was a kind of worldwide quest, so to speak, to come up with the first polynomial time method for linear programs. That was a very big interest in optimization. And the first person to do that was Kachikan, who had the first polynomial time algorithm for linear programs that was essentially a variant of the ellipsoid method. Another ellipsoid method is another very beautiful algorithm that's kind of classical that we're not going to learn. And this was both an enormously important contribution theoretically and also something that was practically not very useful. So nobody really got anything out of this. It was a very weak algorithm in practice. So Karmakar is the person who's credited with the first interior point method, really probably ever, but specifically polynomial time interior point method for linear programs. And this was actually fairly efficient. This made a very big difference in practice. So it was a very important contribution to optimization. It was patented, and actually the patent expired in 2006. So I think that somehow he held on to this patent for a very long time. And the one that we know today, okay, or let's say one that's more similar to the one that we're using today, is the Newton-based interior point method of Renegar. And for a long time, this had the best known complexity for solving linear programs, really for solving quadratic programs, for solving general convex problems, smooth convex problems subject to smooth inequality constraints and linear equality constraints. This had the best known complexity. The one where it's really very close to the primal dual interior point method that we're going to see next time. And I think kind of remarkably, only a short number of years ago, in 2014, Yin-Tat Lee and Aaron Sidford came up with a cutting plane method, so completely different, non-interior point method, that actually achieves a better worst-case complexity for general convex problems. So that's fascinating, and maybe the case that in the future, instead of teaching interior point methods, we'll be teaching cutting plane methods more carefully. But at this point, this work is so complicated that I think it's still kind of circling the optimization community, and we're not teaching it yet. But modern state-of-the-art solvers, as I mentioned already, they typically use the interior point methods. So if you use Cplex is a very popular commercial linear program solver that's actually free for academic use. A lot of these things are free for academic use. And they typically use interior point methods, but they actually also typically employ simplex methods. And they decide based on somehow heuristics which one to deploy. They may also deploy both or something, give them 2 threads, and then kind of choose which one to go with. So there's typically a very complicated decision tree that happens with these commercial solvers for deciding on the algorithm. But let's say the simplex method is still actually used widely as well as interior point methods. So that was just some history to motivate what we're studying. And when we come back on Wednesday, we'll learn the other interior point method, the primal dual method. So I will see you guys there.